Good morning, students. Today we will be continuing our discussion on the topic of thermodynamics further. Today we will be studying about an important thermodynamic process, that is isothermal process. What is an isothermal process? An isothermal process is one in which pressure and volume of the system change but temperature remains constant. Now, to carry out isothermal process, a perfect gas is contained in a cylinder having conducting walls, and the gas is compressed or allowed to expand very slowly. When the gas expands, cooling will occur due to the absorption of heat by the gas. But as the gas is allowed to expand slowly, therefore, before the temperature of the gas falls, heat is conducted into the cylinder through the conducting walls from the surroundings. Hence, when a gas is allowed to expand slowly, the temperature of the gas will remain unchanged. On the other hand, when the gas is compressed, heat will be produced. Now, since it is compressed slowly, the heat developed in the gas leaves to the surroundings through the conducting walls before it could increase the temperature of the gas. So, if the gas is compressed slowly, the temperature of the gas will remain unchanged. So, therefore, for an isothermal process to take place, the cylinder should have conducting walls, and secondly, the gas should be compressed or allowed to expand very slowly. Equation of isothermal process. For 1 mole of ideal gas, we have PV to be equal to RT. Now, as in an isothermal process, temperature remains constant, therefore we can write down PV to be equal to constant. Now, this is the equation of an isothermal process for an ideal gas. So, if P1 and V1 are the initial pressure and volume, and P2 and V2 are final pressure and final volume, then we can write down P1 V1 to be equal to P2 V2 for an isothermal change. How can we apply first law of thermodynamics to an isothermal process? The internal energy is function of temperature only. Now, since temperature does not change during an isothermal process, there is no change in the internal energy of the gas. So, we can write down du to be equal to 0. Therefore, when a gas undergoes an isothermal change, that is whether it is an expansion or compression, there is no change in the internal energy of the gas. So, from the first law of thermodynamics, we have dq equal to 0 plus pdv, or we can write down dq to be equal to pdv. So when the gas is undergoing expansion, in such a case dv and hence pdv is positive, and consequently dq will also be positive. So if a gas is to be expanded isothermally, then an amount of heat equivalent to the work done by the gas will have to be supplied to it from the external source. Now when the gas undergoes compression, in such case, since the volume is decreasing, so dV will be negative. Accordingly, PdV will also be negative, and likewise dQ will also be negative. Therefore, if a gas is to be compressed isothermally, then an amount of heat equivalent to the work done on the gas will have to be removed from it. Let us find out an expression for work done during isothermal process. For this, let us consider this particular setup. Let us consider 1 mole of a perfect gas contained in a cylinder having conducting walls and provided with a conducting and frictionless piston. Let at any instant the pressure, volume and temperature of the gas be PV and T respectively. This is the initial state. Let at any instant the pressure, volume and temperature of the gas be PV and T. Suppose that the piston moves through an infinitesimally small distance dx at constant pressure P. Then small amount of work done dW should be equal to PA dx, that is equal to P dV, where small a is the area of cross section of the piston. Therefore, when the system goes from the initial state A to the final state B, amount of work done W should be equal to integral V1 to V2 P dV. Now, for 1 mole of ideal gas, PV is equal to RT, which implies P to be equal to RT by V. So now substituting in the above equation, we get W to be equal to integral V1 to V2 RT by V dV. Now during an isothermal process, the temperature of the gas remains constant. So we can write down, for isothermal process, if we take out both the constant terms outside, we get 1 by V dV. So on solving this, we get, for isothermal process, so this should be equal to, and substituting the limits, so therefore for isothermal process, this will be equal to RT log of V2 by V1, or on changing to the common base, we get 2.303 RT log of base 10 V2 by V1. This is expression for the work done during an isothermal process for 1 mole of an ideal gas when its volume changes from V1 to V2 at constant temperature T. Now for an isothermal change, we know that P1 V1 is equal to P2 V2. So this implies that V2 by V1 is equal to P1 by P2. So therefore we can also write down work done for isothermal process to be equal to 2.303 RT log 10 base P1 by P2. This is expression for the work done during an isothermal process for 1 mole of an ideal gas when its pressure changes from P1 to P2 at constant temperature T. So if m is molecular weight of the gas, then work done during an isothermal process for 1 gram of ideal gas. So this can be written as equal to 2.303 small r T so small r is the gas constant. So this shall be the equation for work done of an isothermal process in terms of the gas constant. This will be all for today's class. Thank you.